Okay, so this is lecture 33. I'm going to relate the infinitesimal generator matrix we derived last time to the matrix through the transition function P. So just to give you some of the terminology, just to remind you some of the terminology, so our transition function P of t is described as the probability that we start at x0 in state I and we transition to state j in time t. So remember last time we derived the infinitesimal generator matrix, and basically it was defined as p prime of 0. So we can think about our infinitesimal generator matrix as having our transition rates here and our off-diagonal elements, and then basically the way that you find the diagonal elements is that the columns have to sum to 0, or on the diagonal elements are just equal to the sum of all of our transition rates. Okay, so for example, with our process process, now going from P to Q, so this is just an example going from P to Q, and we're going to talk about what if we have Q and can we get back to P. But here, for our process, remember we had our probability at delta t. Remember, for the process, we talked about the number of arrivals, and so you had, you start with 0 arrivals, and you can go to 1 arrival, or you can stay at 0 arrivals in some infinitesimal time delta t. So we can actually think about getting our Q matrix by just looking at 1 over delta t times P of delta t minus the identity. So if we do that, if we find P of delta t minus the identity, and we just have this minus lambda delta t on our diagonal, and then the lower diagonal is lambda delta t. We divide by lambda delta t, and here again we just have our transition rates. Remember, you transition from state 0 to state 1 at a rate lambda. So here's our transition rates, and our diagonal elements are just negative that. And so also remember that you can only go from state 0 to state 1, from state 1 to state 2, or you can stay at state 1. Okay, so another way of actually finding the process, if we had our transition function, we could have just taken our derivative. So you remember we had our P of t for any time t. So what's the probability that if we started in state 0 after t increments of time, we'll have 2 arrivals, 3 arrivals, etc. We will have counted this. And so if we think about here and take the derivative of p prime, then we can just plug in t equals 0, and we get the exact same matrix as we had before. So just reminding you here how this is the exact same matrix. So t equals 0, then this part's going to be just 1, so we have negative lambda. T equals 0, this part's gone, so we just get this part, which is going to give us lambda, and then we get 0 below that. And again, we're going to have minus lambda, lambda, and we have zeros out below that. Okay, so remember our registration line example, we had this schematic, we had our holding time parameters, and we were able to use all of our transitions. We were able to find our transition matrix here, and we actually found our transition matrix, our embedded chain transition matrix from using our rates. And so we did that last time. We didn't start with P, we actually found P based upon our rates. And so we had this infinitesimal generator matrix Q, which we just have our rates on here, and then on our off diagonal it would have the sum, the negative sum of those. So remember here, going from 0, we can only go from 0 to 1 at a rate of 1/4, so that's why we have this 1/4 here. This is just the negative of it. Then we're in state 1, we can go to state 0 at a rate of 1/5, so there's our rate. We can go to state 2 at a rate of 1/4, there's our rate. And then the negative sum here is this negative Q1 basically, is on our off diagonal. So here we have just our negative Qi, and then we have our transitions rates Q. In this case, it would be Q01. Here, this is Q, let's see, I'm sorry, this one would be Q10, and this would be Q01, etc., etc. So now the question is, last time we actually went from this and we found our P just by using some of the things that we know. So let's figure out how we can actually do this in general. So most of the time, like I said before, most situations you identify transition rates first. you don't really think about the transition function. First, you think about the transition rates. And so we want to figure out how we can go from our transition rates, our matrix Q, and derive the function P of t. So for our continuous time Markov chain, the relationship between P of t and Q satisfies this forward differential equation dP dt is equal to Q times P. So remember, the matrix multiplication is not commutative, so this Q is on the left-hand side and this P is on the right-hand side. Physics and chemistry, this is often referred to as the master equation or the chemical master equation. And this actually comes up in some of how you actually code continuous time Markov chains. This master equation does. Another way that we can think about this is it also satisfies the backward equation, so we actually can, our derivative is equal to P of t times Q. Remember, Q times P is not the same as P times Q, but it does satisfy this differential equation here. Okay, so how does that help us in terms of finding our matrix P if we're given our state Q? Well, here think about having this matrix Q here. This is an example. I'm going to show you how you can use this differential equation to find your P matrix. So what this tells us is that if we're looking for P, we're given Q, we have this relationship here. So if we look at our first entry here, we're going to have the derivative of P11 prime here is equal to, so what corresponds to this first entry is going to be the first row times the first column, so we're going to have Q11 P11 plus Q12 P21. Let's fill in what we know about our Q's. So what we know about our Q's is our Q11 is minus lambda, our Q12 is mu. And then we can also, we know something about our P's, right? So this is our probability transition matrix, and so the columns are going to sum up to 1, so we can write P21 as 1 minus P11. Then notice what we have here. If we look at this and we look at this side, we have everything in terms of P11. We just have a differential equation in terms of P11, which can actually be solved using an integrating factor from differential equations. So just to remind you a little bit about differential equations and how to use an integrating factor, if you have any differential equation of this form, then you can find what's called an integrating factor. And this should be the integrating factor, not the integrating. The integrating factor is e to the integral of a of x dx. So what's nice about this is we multiply both sides of this differential equation by our integrating factor. The left-hand side ends up being something really nice. So we multiply both left and right-hand side, then the left-hand side is just ix times y. So think about here, if I multiply this out, then what we end up having is multiplying, this is just the product rule here, so we get this part. And the right hand side we just have I of x bx, so we can integrate both sides and find our answer. Okay, so back to our example. Let's actually do an example of implementing this. So here's our example. We find our integrating factor. We said we have e to the, this is our a here, and so we integrate lambda plus mu dt. We just get lambda plus mu t. Multiply both left and right hand sides. The left hand side we can just integrate, and we're left with our integrating factor times our P11. The right hand side we multiply this by our integrating factor, we have this, which we can just easily integrate. The integral of e to the lambda plus mu t is just e to the lambda plus mu t divided by the lambda plus mu. We have to add our constant here. So then we have our form of P11 just by dividing by that e to the lambda plus mu t. We can solve for c by realizing the fact that P11 at time t equals 0 is just 1. So that means that we can find c as lambda over lambda plus mu, which gives us our P11. So if we do the same thing for P22, then we have this form for P22. Finding P12 and P21, we can just realize that the columns sum to 1, so we get our P of t here. So another way that we can think about this is knowing that dP dt is equal to q times p, then we actually have that P of t is equal to e to qt, where this is our matrix exponential. So e to the qt has this infinite sum. So just like you learned kind of in Calc 2, but this is with matrices. But it's nice, you can either look at e to the qt in this way, or if q is nice enough to be diagonalizable, then things work out really nice, because finding e to the qt is as simple as finding our diagonalization. So remember here, D has our eigenvalues on it, S has our eigenvectors, and this is just the inverse of that matrix. And so then e to the qt has this nice form. We just have S, e to the dt, and S inverse. So our example that we just did is actually diagonalizable. So it has eigenvalues 0 and negative lambda plus mu, and these are the eigenvectors. So this is the eigenvector that corresponds to 0, the eigenvector that corresponds to minus lambda plus mu. We put these in our S matrix. So here's our S matrix. We have our e to the dt, so we have e to the 0t and e to the minus lambda plus mu t here. And then this is just our S inverse. So remember how to take the inverse of a 2 by 2 matrix. We have 1 over the determinant. The determinant is mu plus lambda here. So here's my mu plus lambda. And then we switch our diagonal entries, so we have the 1 and the mu. And then we take negative of the off diagonal entry, so we have positive 1 and negative lambda here. We multiply it all together and things work out as they should, and we get the exact same matrix. Okay, so sometimes Q isn't diagonalizable, and sometimes it's hard to figure out what it should look like in the infinite summation form. The nice thing is that we can use maple and sometimes Wolfram alpha to actually find e to the qt. So using maple, this is an example of using maple. So you can use maple just using GoldLab, like the way that you get to MATLAB for the class as well. You can also get to maple. So here, using maple, this is the command. You need linear algebra toolbox here. So you just have to do with linear algebra since you're working with matrices. You form your matrix, so you define Q to be your matrix. So to define Q to be your matrix, you need this dot equals. Then you're going to say it's going to be a matrix. So you put it in parentheses. You have brackets to indicate the matrix, and then brackets separating each of your rows. Then to find your e to qt, you just want your matrix exponential of your matrix Q with parameter t here. So here, this bracket and this bracket indicates my first row, and then my first entry here is this one. My entries are separated by commas. Okay, so next time we're going to actually go back and look at some of our discrete time Markov chain terminology in order to figure out some of our terminology for our continuous time Markov chains.